We know the containers member functions are functions that work on the container's data, and we know the algorithms are also functions that work on containers data. So the question is, could there be any duplicate functions between these two groups? The answer is yes, there are duplicate functions, and there are quite some. Let's first look at the list. List has remove function to remove certain item, and it has a template function remove if, which allows you to provide your own comparison function. It has the unique and template unique, sort, template sort, merge, template merge, and reverse. So these are the list's member functions that has duplicate functions in algorithms. Now let's look at the associative containers. Associative containers have count, which counts the number of certain items, find, to find a certain item, lower bound, upper bound, equal range. Those are the binary search algorithms. So again, these are the functions that has duplicate functions in algorithms. And one thing to note is they don't have the generalized form which allows you to provide your own comparison function like the ones in the list. That is because the associative containers have sorted data. So the comparison function is already defined inside the container. Now let's look at the unordered containers, which have count, find, and equal range. And again, they don't have generalized form that allows you to provide a custom function because they use the hash function to search. So these are the member functions of the containers that have duplicated functions in the algorithms. Now the question is, why? Although these functions and the functions from the algorithm are duplicate functions, and they have the same purposes, they are actually different. They do things in a different ways. And you should not see them as equal because one way is better than the other. So, which one is better then? This is what we want to find out today. First, let's look at an example of unordered set, which is implemented with hash table. We have an unordered set of integer s, and we want to find an item in s. And first, I use the member function. I do s.find4. And we know that takes amortized constant time. It is one big feature of the hash table. Then I use algorithm to find the item of 4. I do it find s.begin, s.end 4. And that takes linear time because the algorithm only takes the data in by the iterators. So the algorithm find only know the data through the iterators. It doesn't know anything about the container. It doesn't know whether the data is stored on a hash table or a binary tree or a contiguous array. So the only way for the algorithm to find the data is starting from the first iterator and then iterate every item until reaching the end iterator and find the item, which takes linear time. So in the first round, the winner is member function. Now let's look at an example of associative container. We have a map of char and string, my map, which contains a lot of data, and we want to find one item in the map. First, I use the member function. I do it mymap.findf, and that takes logarithmic time. It is a feature of associative container. Then I use algorithm to find, and it takes linear time to search for the same reason that we've talked about in previous example. However, this is not the end of the story. when the member function tries to find, it tries to find a key that is equal to f. And when the algorithm tries to find, it not only needs to compare the key of f, it also needs to compare the string that is associated with the key. So the algorithm's comparison function is more complex than the member function's comparison function. The algorithm is taking double penalty in the function's complexity. One is from the number of iteration and another one is from the comparison function. So in the second round, the winner is still the member function. Now let's look at the example of list. We have a list of integer s, which contains a bunch of integers, and we want to remove one of the integer, 4. Since list contains unsorted data, so the only way to find the item of 4 is to iterate through every item in the list. There's no other way around. So the member function of remove 4 takes linear time, and the algorithm of remove takes also linear time. So it looks like we don't have a winner here. But if you take a closer look at how things are done, there is actually a winner. Now we have a picture of the list that contains the integers, and we want to remove the item of 4. First, I used list's member function of remove. The member function does the removal by tweaking the pointers. The forward pointer of 1, which originally pointing to 4, now is pointing to 8. And the backward pointer of 8, which originally is pointing to 4, now it's pointing to 1. And as a result, the item of 4 is removed from the list. Now let's look at the algorithm removal. The algorithm removes the item by copying. It copies 8 to 4, 5 to 8, and 9 to 5. So as you see, the member function only needs to tweak 2 pointers, and the algorithm needs to do a linear number of copying. And the penalty of copying could be very big if the items in list are not as trivial as integers. So back to the code. Although it takes linear time for both the member function and algorithm to find the item of 4, the member function takes constant time to remove the item of 4, and the algorithm takes another linear time to remove the item of 4. So again, the winner is the member function. And there's something more. After the member function removes 4, the content of S is like this. It has 2, 1, 8, 5, 9. The 4 is removed. However, after the algorithm removes 4, the content of S has one more item of 9. If you remember in the picture, the algorithm remove does the removal by copying. So it copies 8 to 4, 5 to 8, and 9 to 5. So the last item of 9 is not removed. It is still in the container, and the size of S is still 6. Why it does that? The reason is the algorithm only knows the data through the iterators. It doesn't know the container, and the container is the only one that can actually remove items. So to complete the task of removal, we have to remove the last item of 9. How do we do that? Fortunately, the function remove returns a iterator that points to the new end of the data. So we need to use a iterator to store that position, and then use the member function of erase to erase the items at the end. Now, S contains the items that we want. It has the same result as the member function of remove provide. So as you see, the algorithm of remove is less easy to use than the member function of remove. Now suppose I want to sort the items in the list. And with the member function, I can use s.sort, and the things will be sorted. And use algorithm, I will do sort s.begin, s.end, and this will result in undefined behavior. Why is that? Because the algorithm sort requires random access iterators, and a list doesn't have random access iterators. It only has bidirectional iterators. So the algorithm sort simply doesn't work. Summary: there are duplicated functions between containers member functions and algorithm functions, and it is preferred to use the member functions over the algorithm functions. The reason is the member functions have the privilege of knowing the internal data structure of the containers, and they can take advantage of that knowledge and finding the most efficient way to perform the tasks. The algorithm function cannot match that. So this is why in general we prefer member functions. I said in general because there are exceptions, and we'll talk about those exceptions in the future. That's all for today. Thank you for watching. Feel free to subscribe to my channel so when I post a new video, you will be updated. Or you can go to my channel's homepage and see what I'm offering today. Bye bye.